Uh, Good morning, everybody. Before starting today's topics, that is big M approach, big M method, let's do one or two problems on the simplex algorithm what we discussed in the last class. Let's take a problem, maximize z equals x1 plus x2 plus 3x3 subject to 3x1 plus 2x2 plus x3 less than equals 3, 2x1 plus x2 plus 2x3 less than equals 2, and x1, x2, x3 is greater than equals 0. If you see here, all the constants are non-negative constants, less than equals constants. So, first let us write down its standard form. The standard form means since it is less than equals type. So, we have to add two more slack variables to make it equality, the constant. So, in standard form we can write down maximize z equals x1 plus x2 plus 3x3 subject to 3x1 plus 2x2 plus x3 plus the surplus variable x4. I am writing the next part after some time. The next one is 2x1 plus x2 plus 2x3 plus coefficient of x4 will not be coming here. We have to add one more slack variable. So, this is equals 2, and in the first constant coefficient of x5 is 0. So, we are writing this is equals 0. Please note this, in the objective function also for these slack variables we are adding a coefficient of 0. So, 0 into x4 plus 0 into x5, where xi is greater than equals 0, I is equals to 1, 2, 3, 4 and 5. So, if you note one thing, by adding these slack variables over here, and if you make the three variables x1, x2, x3 equals 0. So, one solution you will get x4 equals, this is not 0, this will be equals to 3. If I make x1, x2, x3 equals 0, if you put x4 becomes 3 and x5 becomes here 2, and this forms one identity matrix if you consider the coefficients of x4 and x5 after making all these 3 equals to 0. So, x4 and x5 becomes the basic variables and they satisfy the non-negativity constraint. Now, let us come to this one. Whenever you are having this problem, just see this thing, I think it is visible, maximize this one. So, we have written CB, B, XB, B. I am having 5 variables x1, x2, x3, x4, x5. Now, my basic variables are x4 and x5. So, let us write down the coefficients of Cj. Cj x1 is 1, 1, 3, 0 and 0. So, with respect to x4, Cb value, that is coefficient in the objective function, this is 0. Your B value is 3 and 2, these are the B values. Now, the first row will come over here with the coefficients of x1, x2 like this. So, it will be 3, 1, 1, 0, and the next one will be 2, 1, 2, 0 and 1. So, this is the initial table. From the initial table, once I am drawing the initial table from here, now I have to calculate the Zj minus Cj over here. My Zj minus Cj will become Cb into x1 plus Cb into x2, this one, this value minus Cj. Your Zj is Cb into this, 0 into 3 plus 0 into 2 minus 1. So, that it becomes minus 1. Similarly, Cb into in x2 column you add. So, 0 into 2 plus 0 into 1 minus 1, it is becoming 1. Next one is minus 3, the next one will be 0 and afterwards this one also 0. So, most negative column is this one. So, basically your in the next column x 3, because z j minus c j is not greater than equals 0 for all j. Therefore, I have to go to the next table. So, entering vector is x 3 here by this arrow we are showing. So, once we have obtained the entering vector, now we have to calculate what is the ratio to find out what will be the outgoing vector. So, what is the ratio? Ratio will be for this column b divided by x 3, that is 3 divided by 1. So, it is 3. For this case it will be 2 divided by 2. So, this is equals 1. So, the minimum one is x 5. So, x 5 will go out from the basis and x 3 will enter into basis. So, this is the mechanism. So, from this table again we are calculating the next one. If you see the next table, already I have written x 4 is there in the basis. From the earlier table x 5 has gone out and x 3 has been entered. So, your pivot element for this case is this one, pivot element will be this. So, now once you are writing this thing, your C j remains same 1 1 3 0 and 0. Your C b now corresponding to x 4, the coefficient in objective function is 0, but corresponding to x 3 it is 3. Your b value, now I have to calculate what would be the next rows. I have to make the pivot element is as 1 and the other element, that means the other row, the corresponding to the pivot element, this element as 0. So, to make this one as 1 pivot element, I have to divide by 2 throughout. So, it will be 1 1 half 1 0 and it becomes half. And to make this one, I have to make 1 minus 2 divide 2 into half. 2 into half means 1. So, that it becomes 0. So, like this way it will be 3 minus 2 into half. So, it becomes 1. So, 3 minus 2 into half, it will be 2. Likewise, this will be 2. This will become 2 minus half into this, that is it will become 3 by 2. This becomes 0, 1 and minus half, if I calculate in the same way over here. Next, I have to calculate z j minus c j using the same procedure, that is C b into x 1 summation of C b into x 1 minus C j. So, 0 into 2 plus 3 into 1 minus 1. So, that it becomes 2. On the same way it becomes half, this becomes 3 minus 3. So, it is becoming now 0. This 0 into 1 plus 3 into 0 minus 0. So, it is 0 and this one becomes 3 by 2. So, if you see your z j minus c j is greater than equals, z j minus c j is greater than equals 0 for all j. Therefore, we have achieved the optimal solution. What will be the optimal solution? Optimal solution is here, your in the basis only x 3 is present, x 1 and x 2 is not present. Therefore, the decision variables which are not present in the basis, they will become 0. So, x 1 is 0, x 2 is 0 and x 3 this is equals 1. So, this is your optimal solution. If I calculate the z max by substituting in the equation, from here itself you can get it 0 into this plus 3. So, that your z max become 3. Now, please note one thing, the optimal solution is unique in this case, because your z j minus c j is greater than 0 for all non-basic variables. Z j minus c j is greater than 0 for all non-basic variables. Non-basic variables means the other one, that is x 1 and x 2, here non-basic variables, x 3 and x 4 are basic variables. Since for non-basic variables z j minus c j greater than equals 0, and if you see z j minus c j, this is equals 0 for all basic variables. So, Since Zj minus Cj greater than 0 for all non-basic variables and Zj minus Cj equals 0 if you see corresponding to x 3 and x 4, this is equals 0 for basic variables. Therefore, the solution is unique in this case. I will just take one more example which already I have done, just for your sake of convenience I am showing it, so that you can see it afterwards and you can go through this one. If you see, the problem is maximize here a function of 4 variables and I am having 3 constraints and all are less than equals type. So, therefore, we require 3 slack variables x 5, x 6 and x 7. If you see in the objective function in the coefficient, we have made the coefficient of the slack variables as 0. Now, we are making the equality constants in the first one, only x 5 coefficient of x 5 is 1 and coefficient of x 6 and x 7 will be 0. We are making introducing slack variable on the same way you are doing this one. So, here initial basic matrix corresponding to this I 3, that is if you see this portion, because I will make the division variables x 1, x 2, x 3, x 4 equals 0. In that case, you will have only x 5 equals 4, x 6 equals 3 and x 7 equals 3. So, that the basic variables will be x 5, x 6 and x 7. Using the same procedure whatever we have done earlier, I can formulate the corresponding tables. The first table I am showing here, if you see for your convenience I can show you this matrix and this one, so that it will be easy. Coefficients of Cj are 2, 4, 1, 1, then 0, 0, 2, 4, 1, 1, 0, 0, 0. The variables are x 1 to x 7. Here your basis vectors are x 5, x 6 and x 7. So, correspondingly we have written Cb, the columns are being created and on the same way you are calculating Zj minus Cj from here. Once you have calculated Zj minus Cj, if you see the most negative one is the column x 2. Then we are calculating the ratio and ratio we are getting like this way. If you see here, although 4 by 3 is the minimum, so this variable will go out, x 5 will go out, but situation may arise something like this. I wanted to show you for this reason. The ratio this one x br by y rj, this particular ratio, if it is same just like say 3 3, in that case various cases may arise. One case is you can take any one of these two and you can proceed to the next simplex table. Other one case may be once it is equal, in that case it may happen that the solution is degenerate solution you are obtaining in the subsequent simplex table. This degeneracy case will appear whenever you are having the equality in the ratio. We will discuss this degeneracy case afterwards. And then you are forming the subsequent tables. For your convenience, you can use this table, you can do it of your own. I have just written the optimal solution of this. This is not the optimal solution. Optimal solution is x 1 equals 1, x 2 equals 1, x 3 half, x 4 will be 0 and z max 13 by 2. But please note that this particular table whatever I have shown, that is also not optimum table, because here Zj minus Cj is not greater than equals 0 for all j. So, you have to continue in the same fashion, and if you continue in that case you will find that you are getting this particular result. You should do it of your own. Now, let us come to the next one, that is the big M approach. I am just first writing the big M method. In this big M method, what we do? If you have noted one thing, that in the earlier simplex algorithms or the problems whatever we have solved, the constraints are always less than equals type only, and there you have used the slack variable, you have added the slack variable to make it equality. If you remember, if it is of greater than equals type, in that case we told that we will introduce. So, for less than equals, if it is x 1 plus x 2 less than equals 1 and x 1 plus 2 x 2 less than equals 2, what we were doing? We were making x 1 plus x 2 plus x 3 plus 0 into x 4 equals 1 and x 1, this is x 1, x 1 plus 2 x 2 plus 0 into x 3 plus x 4, this is equals 2. So, like this way we are making, and whenever you are making x 1 x 2 as 0. So, your basis variables becomes x 3 equals 1 and x 4 equals 2. This we were making over here, x 4 is equals to 2. Now, the same problem if I write like this x 1. So, this is we have done earlier, x 1 plus x 2 greater than equals 1 and x 1 plus 2 x 2 greater than equals 2. In this case, what we have told earlier, if you remember, we have to add surplus, subtract surplus variable to make it equality. That is, I will write down something like this, x 1 plus x 2 minus x 3 equals 1 and x 1 plus 2 x 2 minus x 4, this is equals 2. Do you see what is the problem in this? The problem here is that if I make x 1 equals 0 and x 2 equals 0, what I am obtaining? I am obtaining basically x 3 equals minus 1 and x 4 equals minus 2 as the. So, this should be my basic variables, but they are not satisfying my non-negativity constraints, because we have told all the decision variables should be non-negative, so they should be greater than equals 0. So, they are not satisfying this condition. So, I cannot formulate the initial basic feasible solution by introducing only surplus variable. I think the concept is clear, that whenever I am making introducing the surplus variable, I am just subtracting to make it equality for the case of greater than equals, and once you are making the negative, you are subtracting. So, by making the decision variables equals 0, the surplus variables will become negative and they will not satisfy the constraints. To overcome this particular situation, for each surplus variable we have to introduce one new variable which we call as artificial variable, This variable we are calling as artificial variable we have to introduce. So, in an LPP, if you are having, say you are taking one LPP with n equations and you have m greater than equals constant. That means, you are considering all the constants as greater than equals type, and how many are there? M greater than equals constants. So, whenever you try to write this into the standard form, in that case you are maximizing z subject to the constants, and constants all will be of equality type. In that case, how many equality constants will be there? There will be total n plus m variables. What is n? I can rewrite it in decision variables, that is your initial decision variables, plus m, this is one part, other part is m surplus variables plus m artificial variables, So, for the constants, equality constants, there will be total n plus m variables. Out of that, n are the decision variables, m surplus variable and m artificial variable. So, what I have to do in this case, what I have to do, that is, I have to get the initial basic feasible solution, I have to make this first n plus m decision variables equals to 0. That means, this one n plus m decision variables should be equals to 0. Once I am making n plus m artificial variables equals 0, then n plus m decision variable plus surplus variable equals 0, then all the artificial variables will take some form like this, a I equals b I, where I equals maybe 1 to m. So, where a I are the artificial variables. To make it simpler for the above problem, what I was discussing, x 1 plus x 2 greater than equals 1 and x 1 plus 2 x 2 greater than equals 2. Once you are having this particular problem, so I have to introduce one slack variable, I have to introduce one surplus variable. So, it will be something like this, introduce one surplus variable and introduce one artificial variable, that is say a 1, this is equals to 0, and this one will be x 1 plus 2 x 2 2 x 2 minus x 4, here a 1 will not be there, but I have to introduce one more this thing. So, this is equals 1. So, this is actually 1 and this will be equals to 2. Your equations, equality constants will be something like this. Therefore, what happens here, whenever you are making to make the initial basic feasible solution, the initial values whenever you are making x 1, x 2, x 3 and x 4 equals 0, I have told n decision variables plus m surplus variable, we are having 2 decision variable and 2 surplus variable. If I am making all 4 as 0, one I will obtain a 1 equals 1 and other one will be equals to a 2 equals 2, and these two are satisfying the non-negativity restriction and you are obtaining the identity matrix 1 0 0 1 form. So, your basic variables will be this one. You have to, so like this way I am making the initial basic feasible solution for this big M method by introducing the artificial variable. Please note one thing, that the above equation whatever you are writing of the form a I equals b I will not be a solution of the original problem, because the original problem and the problem converted problem both are not equivalent. Since the original problem given and after introducing artificial variable whatever problem you are obtaining, these are not equivalent, and therefore, a I equals b I will not be a solution of the original problem. Or in other sense, by in some way I have to remove the artificial variables from my simplex tables. And to remove the artificial variables from the simplex table, what we do, a very large negative penalty we are assigning as the coefficient of the artificial variable in the objective function. Now, we are introducing a large penalty which will be associated with as a coefficient, large negative quantity as which will be associated with the artificial variable in the coefficient of the objective function. So, suppose your objective function is something like this, max z equals 5 x 1 plus 3 x 2 for the earlier problem. So, whenever I will try to write it, convert this one, I will write down max z equals 5 x 1 plus 3 x 2. For the earlier problem, there was 2 surplus variables, their coefficient will remain 0, 0 into this one. But for this case, what will happen? For this problem, there will be some values which will be minus m into some large quantity m into a 1 minus m into a 2, like this. So, m is a very large quantity. So, large penalty we are associating large not only quantity, but I should say large negative value we are associating with the maximizing z function, and therefore, once you are doing it, so in the function I have to remove the artificial variables. I am just coming to this. So, this is the basic approach. Therefore, if I have to rewrite the problem, say your original problem is maximize z equals c 1 x 1 plus c 2 x 2 plus c n x n subject to a I 1 x 1 plus a I 2 x 2 plus a I n x n greater than equals b I is 1 to n, and your x j is greater than equals 0, j equals 1 to n number of decision variables. So, here we have to introduce, since I am having I will be equals to 1 to m, that is m constants are there. Since m constants are there, to write it in the standard form, we have to add m surplus variables and m artificial variables to put it in the standard form. So, equivalent problem after introducing surplus and artificial variables, I can write it in this form. Maximize z equals c 1 x 1 plus c 2 x 2 plus, like this way I am going, plus c n x n plus there will be 0 into x n plus 1, 0 into x n plus 2, we are going 0 into x n plus m. So, this from x n plus 1 to x n plus m, these are the surplus variables which are associated with each constants, and their coefficient is 0 in the objective function. Now, here I have to write down the associate also a large penalty to the corresponding to each artificial variables. So, this will be minus m into a 1 minus m into a 2, like this way, minus m into a m. So, these a 1, a 2, a m, these are the artificial variables associated with the ith constants, and we are associating the very large negative quantity over here. And what will be the constant then? Constant will be subject to a I 1 x 1 plus a I 2 x 2 plus, like this way, a I n x n minus introduce the surplus variable and then add the artificial variable, this is equals to b I, and where your I is 1 to m. Your x j greater than equals 0, where j varies from 1 to, like this way, n plus 1, like this way, n plus m. Your a j also greater than equals 0, j equals 1 to m. So, I think the problem is clear to you. Whenever I am giving the greater than equals constraint, then you are introducing, to make it equality, you are introducing the surplus variable, subtracting, and to make the initial basic feasible solution possible, we are introducing one more artificial variable, which I have written over here, and a large penalty is associated in the coefficient corresponding to each of the artificial variable in the objective function. This modified simplex method basically for solving the LPP when a large penalty is associated is known as this method is known as Big M method, or sometimes we call it as the penalty method, or sometimes we call it as the chance method. So, this method is known as Big M, penalty, or chance method. Please note one thing here, these artificial variables basically they are nothing but the fictitious variables. Fictitious variables means they do not have any physical meaning, neither they have any economic significance. Basically, to make for the computational convenience, we have introduced this concept of the artificial variable. Now, you may ask one more question, that why we are adding a large penalty, or we are associating a large penalty corresponding to the artificial variable in the objective function. The reason is that we have associated it so that this artificial variable can be removed from the simplex table once the artificial variable becomes non-basic variable. We introduce this artificial variable to make or to get the initial basic feasible solution, and these artificial variables will become the basic variables in the initial simplex table. But since we have introduced or assigned a large penalty in the objective function, once the variable, these artificial variables becomes the non-basic variables, we will drop it from our table. So, this simplex algorithm basically what it does, it tries to converge to an optimum solution for which a I should be equals to 0, for which a I should be equals to 0. It tries to converge to a solution for which we can obtain a I equals to 0. You note one more thing, it is very difficult, you may ask again one more question, what will be the value of I? You are telling that M is large, what large, to what extent? It is very difficult to give the specific value of M. Only thing we can say that once you are comparing M with some finite value, always M will be greater than that finite value. This much we can tell that M is sufficiently large such that if I compare M with some finite number, always M will be larger. So, when one thing can be concluded that whenever you are using this big M method and you are using the manual approach, manually you are doing the simplex table, then this approach is good, because you do not have to very specifically to tell what should be the value of M. But whenever your problem will be large means number of decision variables will be much more, number of constraints will be more, you cannot calculate it manually, then you have to use computer, you have to write down some code. Once you are trying to write down some code, in that case you have to specify the value of M. So, there is a problem, whatever value you have specified, there may have some coefficient whose value is greater than M. For this reason, this big M approach is not friendly with the whenever you want to implement your simplex algorithm through computer. For that we have another method, that is the two-phase method, that we will see afterwards. Now, come to the, so let us rewrite whatever we have told already. What is the procedure? The procedure adopted for big M method. I am just writing, it will be easy to remember for you. So, the first step is write the LPP in standard form. Write the LPP in standard form. So, for each greater than equals type constraint, what you will do? You have to add surplus and your artificial variable. So, for each this one you add greater than equals type, to make it equality you add surplus and artificial variable. I have not talked about this, whenever you are having equality constraint, in that case you have to add only artificial variable. You have to add only artificial variable. So, you may ask why already it is equality, why to add artificial variable? This addition of artificial variable is necessary to form the initial basic feasible solution, that is the identity matrix I have to obtain, so that they becomes the linearly independent set of vectors. So, to form the basis for equality also we have to add the artificial variable. Please note this thing. For less than equals you do not have to do anything, because already you have added the slack variable, and for the slack variable coefficient is already 1, that we have seen. So, for constants you will do like this. In the objective function, now in the objective function, assign a very high, within bracket I am writing negative penalty. Please note this one, sorry, negative coefficient, the coefficient will be negative, very high negative penalty you are introducing for each artificial variable. I think it is clear that in the objective function you are assigning a very high negative coefficient or penalty, which will be associated with as a coefficient for each object artificial variable, whereas for each surplus variable the coefficient will be 0 in the objective function, which I am writing. Now, apply the simplex method, apply simplex method to the above problem, or above, I should say above formulated LPP, and derive the optimal solution. I am just writing so that you can see it properly. So, these are the 3 steps which are required for the greater than equals constants. Again I am telling you, greater than equals constants, add surplus and artificial variables. If you have equality constant, you add only the artificial variable. Now, for in the objective function, assign a very high penalty, which will be a negative coefficient corresponding to each artificial variable in the objective function, whereas the coefficient of the surplus variable will be 0 in the objective function, and after that the simplex method, whatever we have learned earlier, use it to obtain the optimal solution. Now, whenever you are trying to find out the optimal solution, one thing is that you will get the optimal solution, but number 1 is you may get or you will obtain the optimal solution. The other situation may become something like this. Again I am writing that at least one artificial variable, is present, is present in the basis with 0 value. Please note this one. We will stop the simplex algorithm whenever this condition is satisfied, Z j minus C j is greater than equals 0. So, your Z j minus C j is greater than equals 0, it is already there, but at least one artificial variable present in the basis, that is in the final table, where Z j is greater than equals 0, and that artificial value corresponds to a 0 value. In that case, we say that optimal BFS is degenerate. Please note this one. We will discuss, as I told you earlier, degenerate case separately. Just we are telling that if artificial variable is present in the basis and it corresponds to a value 0, then your optimal basic feasible solution will be degenerate. The other part, it may happen that at least one artificial variable, at least one artificial I am writing again this thing is present in the basis with positive value, that is, in this case artificial variable is present in the basis, but it corresponds with some non-negative value, that is greater than 0 value. In that case we say that no optimal BFS exists, no optimal basic feasible solution exists. We are not going to the theory of these things, because it will take much more time, we have to cover so many topics. So, please note this thing, once you have converted your problem with greater than equality constraint or less than equals or equality constraint into standard form by introducing slack, surplus and artificial variables, and after that you have assigned a very high penalty corresponding to the coefficient of each artificial variable in the objective function, and you have rewritten your LPP into the standard form. Then when you are applying the simplex method, then you can, three cases may arise. In the last table of the simplex algorithm Zj minus Cj is greater than equals 0, and you are obtaining the no artificial variable is present in the basis, you are obtaining the optimal solution. Second case may be in the when Zj minus Cj greater than equals 0, in the optimum table your artificial variable is present in the basis and its value is equals to 0. In that case we say that the optimal BFS is degenerate, whereas if the artificial variable is present in the basis, but its value is greater than 0, then we say that there will be no optimal solution. So, now let us take one example and let us try to see how basically the problem can be solved. We are writing maximize z equals 3 x 1 plus 2 x 2 subject to 2 x 1 plus x 2 less than equals to 3 x 1 plus 4 x 2 greater than equals 12 and x 1 x 2 greater than equals 0. So, if you see in this problem we are having one negative constant where less than equals type, another constant is greater than equals type. So, for the less than equals type I have to introduce one slack variable, and for greater than equals type we have to introduce the surplus variable as well as the artificial variable. So, whenever you try to write the standard form, therefore, it should be maximize z equals, I am just first writing 3 x 1 plus 2 x 2, the other coefficients I will write once I am getting this, subject to 2 x 1 plus x 2 plus x 3, I will fill it up afterwards. The next one is 3 x 1 plus 4 x 2. So, here there is no slack variable. So, 0 into x 3. You have to introduce one surplus variable, subtract one surplus variable. So, minus x 4 plus you have to add one artificial variable plus x 5, this is equals to 12 is there. So, x 3. So, in this case coefficient of x 4 will be 0 and coefficient of x 5 will also be 0. This is equality into 2. So, the constants are written like this. Now, about the objective function, maximize z equals 3 x 1 plus 2 x 2 plus the coefficient of the slack variable will be 0, the coefficient of the surplus variable will be 0, but the coefficient of the artificial variable which is x 5, that is minus m, where m is very large. So, you had this problem. Now, this problem is converted into the equivalent problem like this, maximize z equals this one subject to this, and of course, your x 1, x 2, x 3, x 4 and x 5 all are greater than equals 0. So, what will be your initial basic feasible solution? Initial, to obtain the initial basic feasible solution, you are making x 1 equals x 2, this is, and x 3 all as 0, no, I am sorry, x 1 and x 2 is 0. So, that you are obtaining x 3 equals 2, 1 is x 3 equals 2, and from here you are getting, and x 4 is of course 0. Another one, from here you will obtain x 5 equals 12, because if you see coefficient of x 1 is 1 here, here 0, for x 5 it is 0, it is 1. So, they are forming the identity matrix. So, by making x 1, x 2 and x 4 equals 0, you will obtain the identity matrix. So, by making these variables as 0, your initial basic variables will be x 3 and x 5. So, once you have done it, let me see, I think it will be clear. Okay. The problem is, your problem is z equals this one. So, therefore, your x b is x 3 and x 5 as we were telling. So, here also it will be a 3 and a 5. What will be your C j? Your C j, this is actually the C j. C j will be 3, 2, 0, 0 minus m, the coefficients of x 1, x 2, x 5 in the objective function. So, it is 3, 2, 0, 0 minus m. Therefore, it will be, your C b will be a 3, coefficient of a 3 is 0, x 3 is 0 and x 5 is minus m. So, now write the coefficients for the first constants. Your value of b is 2 and 12, whatever is there on the right hand side. So, it becomes 2, 1, 1, 0, 0, whereas this becomes 3, 4, coefficients you are writing 0, minus 1 and 1. So, this is the initial table. By writing the coefficients for the first constant and second constants, you are writing this. Please note that x 3 and x 5 are the initial basis. So, once I have done this one, now this is not required. So, I can write down this, your z j minus c j we can calculate. It will be 0 into 2, this one, plus minus m into 3, that is minus 3 m, minus c j is minus 3. So, it becomes minus 3 m minus 3. Similarly, for the second case, 0 into 1, 0, minus 4 m minus 2. So, it becomes minus 4 m minus 2. For the next one, this is 0. For this one, 0 minus, no sorry, this is 0. For this one, 0 plus m minus 0. So, it is m. For this case, m minus m. So, minus m plus m. So, this becomes 0. So, since m is very large, therefore, the most negative quantity will be this one, or in other sense your x 2 will be the entering vector. Once x 2 is the entering vector, now you can calculate what is the ratio, that is b by x 2. So, for the first row it is 2 by 1, which is equals 2. For the second one it is 12 by 4, which is equals 3. The minimum ratio is this one. So, your outgoing will be x 3. So, and entering will be x 2, and this is your pivot element. That means, I have to make this one, I am sorry, not this, I am very sorry. This is the row which is going out. So, this one is the pivot element, not this. So, your now in the division variables, in the basis x 3 will be out, instead of that you will have x 2 and there will be x 5. This is okay, a 2 and you will have a 5. Your C j is 3, 2, 0, 0 minus m. Now, the procedure is same, corresponding to x 2 it is 2, corresponding to A5 it is minus m. The if you see already this is 1. So, I can directly write down this row without making any calculation. So, it is 2 2 1 1 0 0. So, this will be 1 minus 1 by 4 into 1 by 4. So, that this becomes 0. So, it will be 2 minus for B case it will be become 2 minus this. So, it will be 4. I am just writing now on the same way you can calculate 0 minus 4 minus 1 and 1. Once I have obtained this, now I can calculate Z j minus C j, again 4 2 into 2 minus m minus 5 and this way minus 3. So, it will become 5 m plus 1, this is 0, this will become 4 m plus 2, this is 0, this is m, this is 0. So, if you see here, one thing you should note now, Z j minus C j is greater than 0. So, here the artificial variable is present in the basis. Therefore, this will have no feasible solution. Please note this one. Since artificial variable is present here without 0 value. So, with some non-negative value or not equals 0. So, this will have no feasible solution. Since the artificial variable x5 is present and whose value is greater than 0. So, no feasible solution will occur. Now, let us take another example. Maximize z equals x1 plus 5 x2 subject to 3 x1 plus 4 x2 less than equals 6, x1 plus 3 x2 greater than equals 3 and x1 x2 greater than equals 0. I am not explaining the entire thing, I am just writing maximize z equals x1 plus 5 x2, then for the slack variable this is x3, for the surplus variable x4 and your x5 I am writing here for the artificial variable subject to 3 x1 plus 4 x2 plus x3 plus 0 into x4 plus 0 into x5, this is equals 6, x1 plus 3 x2 plus 0 into x3 minus x4 plus x5 equals 3. Your xj is greater than equals 0, j is 1 to 5. So, your initial basic feasible solution will be x3 equals 6 and x5 equals 3 by making the other variables as 0. So, x3 equals 6 and x5 equals 3. So, in the same way now we can form a table. This is your Cj. We can form the table. I am directly now I am writing 1 5 0 0 minus m. Your initially you are having the basis is x3 x5 a3 x5 and it will be associated with 0 and minus m. Here directly you write down from the first constant, that is b is 6 and 3. This will be 3 4 1 1 0 and this will be 1 3 0 minus 1 0. On the same fashion, first calculate Zj minus Cj. If you calculate it, you will get this value. I am not explaining because now I think you are familiar with this. So, the value will be this thing. Once you are obtaining this, the most negative one is this thing, the variable x2. So, now make the coefficients for this one 6 by 4, that is 1, this one and this is 1. So, this one is this, outgoing will be x5, therefore, you will have this pivot element is 3. Once you are obtaining this, again you calculate the Cj 1 5 0 0. Once x5 is out, Actually, now here you see we are dropping the artificial variable x5, because now x5 is not a basic variable, but it is a non-basic variables. So, your xb is x3, x2, this will be a3, a2. So, corresponding to this you will have this one. So, again I am writing directly 1/3 1 0 0 for have I written correctly 1/3 1 0, this will be minus 1/3. For this one it will be 2 5/3, you can calculate 0 1 4/3. Once you are calculating zj minus cj by the same process, you will obtain 2/3 0 0 minus 5/3. So, still one is negative. So, your x4 will be the entering vector. If you calculate this one, this is 1.5, this is negative. So, you cannot calculate. So, your outgoing will be a3 and your pivot element is this one. Once I have obtained the pivot element as 4/3, I can proceed to the next table, that is Cj. Here your case will be, there will be x4 and x2. Instead of x3 from the earlier table, x3 is going out and x4 is entering. So, x4 x2, so it is a4 a2, your Cj is 1 5 0 0. So, it is 0 and 5. So, by making pivot element as 1, and if you calculate you will get this data set, you can check it of your own. 3/4 1, it will be 3/2, 3/4 1, 1/4 and 0. Zj minus Cj, if you now calculate, you will obtain 19/4, 0, 5/4 and 0. So, now all your Zj minus Cj is greater than equals 0 for all j. So, what is the optimal solution? Your decision variables was x2 and x1, but x2 is present in the basis, x1 is not present in the basis. So, your optimal solution is your x1 is not in the basis. So, x1 is 0, x2 is 3/2, and if you calculate z max, your z max will become 15/2. Again, if you see your zj minus cj is greater than 0, that is, if you see zj minus cj corresponding to x1 and x3, zj minus cj is greater than 0 for non-basic variables, whereas for basic variables x2 and x4, zj minus cj is 0. So, you can say that the optimal solution is unique. Thank you.